Okay, so let me start again with an idea of a vector space, which is the main topic in linear algebra. So we have examples of vector spaces, but let me start with the abstract definition of a vector space. A vector space over a field F, and F is either the real numbers or the complex numbers, is a non-empty set V whose elements are called vectors with two operations. We have the operation of vector addition and the operation of scalar multiplication. And vector addition has the property, the following property. So to all vectors u and v in the set V, this is notation for V is the set of vectors, and this means is an element of or member of. There is assigned the vector u plus v in V. And in scalar multiplication, to all vectors v and v and all elements of the field, there is the vector a times v in the vector space, right? And the elements of a field are called scalars. So in linear algebra, scalar is just a number. So there are two operations in a vector space. You can add vectors, and you can multiply a vector by a scalar. And various properties have to be satisfied. So there's a long list of them, and they're all written out completely in detail in the book. So I'll just write them down quickly and say what they are, but you have to study the book to really follow this. Addition is commutative. So u plus v is u plus v plus u for all vectors. Addition is associative. If you have vectors u, v, and w, you can add u plus v to get a vector and then add w to that.
Yeah, Professor.
Or you can add v plus w and add u to that, and you always get the same thing. So this is the commutativity property. And this is associativity for vector addition. The vector space is always non-empty, and in particular, there is a zero vector in the vector space, which has the property that if you add 0 to v or v to 0, you always get v. So it's just like the number 0 in addition, but this is not a number, this is a vector. So this is the additive identity. And every vector also has an additive inverse. For every v in the vector space, there exists a vector w in the vector space such that v plus w is 0. And w is called the additive inverse of v. And it's a nice exercise to show not only that every vector has an additive inverse, but it has a unique additive inverse. So the additive inverse is uniquely determined. And how do we prove that? Right, this is a statement, an assertion, so it requires a proof. If v plus w1 is 0 and v plus w2 is 0, I want to show w1 equals w2. And how do we do that? Well, let's see.
You have two equations equal 0, right?
What?
You have two equations equal 0, then both of them must be equal, and then you cancel b.
Well, no, you can subtract. Is that what you mean?
Yes.
So I'm proving that you can't just say then you subtract at this point, because we haven't even defined subtraction.
I got it. Thank you.
Okay. But what we can say is the following. Let's see, W2 is the same as W2 plus 0, because 0 is the 0 vector. And 0 can be written as V plus W1 by this equation. By associativity, this is the same as W2 plus V plus W1. This is just, I'm not changing the order, I'm just changing the parentheses. This is associativity. But W2 plus V is the same as V plus W2 by commutativity, and plus W1. And V plus W2 is 0, so this is 0 plus W1. And the 0 vector added to W1 just gives you W1. So this is a proof that W2 equals W1. So it's nice to learn how to prove things in mathematics and in linear algebra in particular, and this is a nice proof. And scalar multiplication has certain properties. So what are some properties of scalar multiplication? First of all, the number 1 is in every field. 1 times v equals v for all vectors v. And if we take, so for all scalars A and B in the field and V in the vector space, If you take A times B, you can multiply that in the field times the vector V. That's the same as A times multiplying that into the vector B times V. So this is a kind of associativity for scalar multiplication. And we have distributive laws. So for all A and B scalars in the field and U and V vectors in the vector space, A times U plus V is AU plus AV, and A plus B times V is AV plus BV. So there actually are two different distributive laws that have to be satisfied in a vector space. So we have already seen several examples of vector spaces. The simplest is Fn, which is the set of all n tuples of elements in the field. And we define addition of vectors in this case. If U is x1 up to xn, and V is y1 up to yn, then U plus V, which is x1 up to xn plus y1 up to yn, we just add coordinate wise, x1 plus y1, x2 plus y2 up to xn plus yn. And if we take A in the field, A times the vector V, that's A times y1 up to yn, you just multiply every coordinate by the same number A. So this is one very important example of a vector space. And F can be the real numbers or the complex numbers. And if you want to get carried away, you could also think about F infinity. So these are vectors of length n. What about infinite vectors? You could look at all infinite sequences, x1, x2, x3, xn, and so forth. This is all infinite sequences. And you can define addition and scalar multiplication the same way. You add coordinates when you're adding two sequences, and you multiply every coordinate by the scalar A when you're doing scalar multiplication. Okay. But we've seen other vector spaces. For example, in calculus, suppose you let V be the set of all functions on the unit interval where F is continuous. So in calculus, they tell you the sum of continuous functions is continuous, and the product of continuous functions is continuous. So this is a vector space over the field R. When we say a real vector space, we mean a vector space where the scalars, the field, is the real numbers. Okay? This is very important in mathematics. So I mentioned, or someone asked about subtraction a few minutes ago. We remember we proved given V in the vector space, there is a unique vector W in the vector space such that v plus w is the zero vector. And because w is unique, we can write or define the vector minus v is w. So minus v is the vector, which is the additive inverse of v. And we can define subtraction of vectors as follows. U minus v is u plus the vector minus v. Minus v is the additive inverse of v. So every vector has a unique additive inverse, and that's how we define subtraction, like this. Okay. So there's some more simple properties of vector spaces that hold for every vector space. So some more properties. So these are not axioms. These are things we will deduce from the definition of a vector space. So if we take 0 in the field and v in the vector space, 0 times v is 0. This is the 0 vector. I'm just going to write it like this to emphasize that this is the number or the scalar 0, and this is the vector 0, right? So if you take any vector and multiply it by the number 0, you get the 0 vector. And how can we prove that? Proof. We use the fact that 0 plus 0 is 0. So what does this imply? 0 times the vector v is 0 plus 0 times the vector v. And by the distributive law, this is 0 times v plus 0 times v. So 0 times v is a vector, and let w be its additive inverse. So 0 times v plus w is 0v plus 0v plus w. I'm just adding w to both sides. And by distributivity, this is 0v plus 0v plus w. But if w is the additive inverse of 0v, this says that 0v plus w is the 0 vector. So this is the 0 vector equal to 0v plus the 0 vector, which is 0v. End of proof. Take any vector v, multiply it by the number 0, you get the 0 vector. And the similar property holds if you take the 0 vector and multiply it by any scalar. So if you take any scalar a and the 0 vector in the vector space, I claim a times the 0 vector is the 0 vector. And the proof of this statement goes as follows. 0, the 0 vector is 0 plus 0. So this implies that a times the 0 vector is a times the 0 vector added to itself. By distributivity, this is a times the 0 vector plus a times the 0 vector. Suppose I let w be the additive inverse of a times the 0 vector, whatever that is. So a times the 0 vector plus w is a 0 vector plus a 0 vector plus W. By associativity, this is A times the zero vector, A times the zero vector plus W. But this says that A times the zero vector plus W is the zero vector. So this is the zero vector. And this is the zero vector. And the zero vector added to anything is the anything. So this is A times the zero vector. And if you look at this, what you see is A times the zero vector is still the zero vector. So that's a nice proof of this. And there's one last assertion I want to prove, which is that for every vector in the vector space, if I take the vector and multiply by the scalar, the number -1, I get the vector minus V. So how can I prove this? Well, if I take -1 times V plus V, that's the same as -1 times V plus 1 times V. Of course, one of the axioms of scalar multiplication is 1 times the vector is the same as the vector. But then I can use the distributive law. This is -1 plus 1 times V. This is by distributivity. And -1 plus 1, these are numbers. -1 plus 1 is 0. And we just showed that 0 times any vector is the zero vector. So -1V is the additive inverse of V, which is, we prove that's unique. So -1 times V is minus V. Okay. So these are very pretty examples of proofs in linear algebra. Okay, so now the topic for the day is chapter 1C, which is subspaces. And a subset U of a vector space V is a subspace if U is also a vector space with the same operations of vector addition and scalar multiplication. It inherits from V. So the first example that's given in the book is if we let V be F3, which is all triples of scalars, and we let U be the set of all triples, but where the third coordinate is 0, U is a subspace. So we have, first of all, U is contained in V. So U is a subset of V. And if we take x1, x2, 0, and y1, y2, 0 in U, and we add them, we add coordinate wise, x1 plus x1 plus y1, x2 plus y2, 0 plus 0 is 0. This is still in U. So the set U is closed under vector addition. And if we take a scalar A times a vector in U, we get ax1, ax2, and the third coordinate is still 0. So this is in U. So this set U is closed under vector addition and scalar multiplication. And you can check all the properties are satisfied. The 0 vector, which is 0 times 0 times 0, is certainly in U because its third coordinate is 0. And in fact, these conditions are the only ones you need to check that a subset of a vector space is a subspace. So let U be a subset of V. So this notation means subset. If 0 is in U, and if U is closed under scalar multiplication and vector addition, then U is a subspace. For example, if U is a vector in U, U is closed under scalar multiplication, so -1 times U is in U, and -1 times U is minus U. So the set U contains the additive inverse of all of its elements. Okay. Any questions about this? All right,
But,
now, so is there a question?
yes, just to prove like a subset, a set is a subset of another one. We have to prove the 3 different parts, right?
Right, you have to prove that it contains the 0 vector, it's closed under scalar multiplication, and it's closed under vector addition. That means that if you take 2 vectors in U, the sum is in U. And if you take a vector in U and a scalar, the scalar product, the scalar multiplication is also in U. So those 3 things have to check, but then you don't have to check all the other requirements of a vector space. They're satisfied automatically.
Okay, thank you.
Okay, now, oh, by the way, let's just look at some pictures. So the first example I gave of a subspace, if you take V to be R3, so this is XYZ space, 3-dimensional space. And if you take U to be the XY plane. That's just this plane in three-dimensional space. So U is all the points X, Y, 0. So this is U. And this is the ambient space, R3. So if you just think of the XY plane sitting in R3, that's an example of a subspace. Suppose you take R2 to be your vector space. And you take U to be the x-axis. That's all points x comma 0. That's a subspace. Suppose you take the line y equal x in the plane. This is the line y equal x. So what a set of vectors are on this line? U is the set of all vectors where y equals x, x comma x. And then I can check, first of all, 0, 0 is in U, right? Two coordinates are the same. If x, x, and y, y are in U, and you add them, you get x plus y. Again, they're the same. So this set is closed under vector addition. And if you take any scalar, A, in this case R, the real numbers, A times x comma x is ax comma ax. So the points on this line are closed under scalar multiplication. So this is another subspace. And in fact, you don't have to take the line y equals x. You can take any line, but it has to go through the origin because 0, 0 has to be in the subspace. So if you take the line y equals mx, this is just a line with slope m. So U is the set of all points x, mx. So this is the line going through the origin with slope m. And again, you can check. This contains 0, 0. It's closed under vector addition and it's closed under scalar multiplication. So that's a subspace. Oh, I should give one other example of a subspace. If I take U to just be the 0 vector contained in any vector space, this is called the 0 subspace. And it is a subspace. It's closed under scalar multiplication because any number A times the 0 vector is the 0 vector. And it's closed under vector addition. 0 plus 0 is 0. So you always have the 0 vector, the 0 subspace of a vector space. And of course, the space itself is a subspace of itself. So every vector space always contains itself as a subspace, and the 0 vector is a subspace.
Professor, can you please explain the last part?
The 0 subspace?
Yes,
Sure.
From the
Okay.
scalar.
So
Thank you.
suppose we let 0 be the 0 vector in a vector space V. So, and let U be the set that consists of just that one vector 0. So first of all, the 0 vector is an element of U, because U is in fact it's just the 0 vector. Second, for all scalars A times the 0 vector is the 0 vector. So U is closed under scalar multiplication. And for all vectors U and V in U, what is U plus V? Well, the only vector in U is 0, so these are both the 0 vector. And you add the 0 vector to itself, you get 0, which is in U. So U is closed under vector addition. Okay. Good.
All right, thanks.
Yeah. Now, it's interesting for many reasons to know the subspaces of a vector space. And given some subspaces, you can construct more. So more generally, I want to define the sum of arbitrary subsets of a vector space. So suppose my vector space is V, and my subsets, I can have 2, 3, 4, 5 million, doesn't matter. Let's say I have M subsets, not necessarily distinct. So the sum U1 plus U2 plus U3 and so forth up to U sub M, this is the definition. This is all vectors that you can write in the form U1 plus U2 up to U sub M, where the vector Ui is in the set U sub I for all I from 1 up to M. So what this means is take all possible sums of a vector in U1 plus a vector in U2 and so forth up to a vector in U sub M. That's this sum set. And so here's a nice example. Suppose I take V to be F3. And I take U to be the subspace, the equivalent of something like the x-axis, everything in the form x0, 0 for x and f. And I let W be something like the y-axis, everything 0, y, 0 for y in f. So if you think of this picture, this is F3. This is U, and this is W. Oops, sorry. This is W. And what is the sum U plus W? It's the sum of all vectors of the form x0, 0 plus 0, y, 0 for all x and y in the field. But when you add these two vectors, you get x, y, 0. So what is this? This is a subspace. And it is exactly what we would think of as the XY plane. So if you take this one-dimensional subspace and this one-dimensional subspace, you add it, you get this plane, which looks like a two-dimensional subspace. Okay. Now, this is an interesting example because here U and W are not arbitrary subsets of the vector space, but each of them is a subspace. And when I add them, I get another subspace. So these are actually subspaces, and this is also a subspace. And this is actually a theorem so in the book, this is 1.39. Says if U1, U2 up to U sub M are subspaces of V, then if I add them, I take the sum set, is first of all, it's a subspace of V also. And is in fact the smallest subspace that contains all the subspaces U1 up to U sub M. Okay. So how can we prove this? So here's the idea somehow. Here's a kind of a picture. Here's V. And sitting inside of V, we have U1 and U2 and U3, all these different subspaces. And one thing we know for sure is the zero vector is in U sub I for all I, because part of the definition of a subspace is that it contains the zero vector. So the zero vector is in all of these subspaces. So if I add 0 plus 0 plus 0 M times, which is 0, this is in U1 up to U sub M. So this sum contains the zero vector. The sum set, each of the summands contains the zero vector. So 0 plus 0 plus 0, which is 0, is in this. So this sum set does contain a zero vector. What about being closed under vector addition and scalar multiplication? So suppose U and V are two vectors in the sum set. So this means that U is U1 plus U2 up to u sub m with all the u sub i's in the set u sub I. And v is a sum v1 plus v2 up to v sub m, where all the v sub i's, each v sub I is in the subspace capital Vi. Sorry, in UI, they're all in UI. Right? But this means that UI plus Vi is also in UI for all I. So if I take u plus v and I add them, just rearranging the terms, because every addition is commutative, this is u1 plus v1 plus u2 plus v2 up to um plus vm. And this is in u1 up to u sub m. So this set is closed under vector addition. And if I take u, which is u1 up to u sub m in this sum set, and I take a scalar a in the field, ui in capital in the subspace ui means a ui is in u sub I for all I, and au is a times u1 up to u sub m, and by distributivity, this is au1 and so forth up to aum. This is in u1 up to u sub m. So u1 up to u sub m is a subspace. And of course, as for example, u1 is contained in u1 up to u sub m, because if we take any vector u sub 1 in u1, u1 plus 0 plus 0 plus 0, do this m minus 1 times. That's u1 is in u1 up to u sub m. And the same argument holds for all of the u's. So this subspace contains each of the subspaces u1 up to u sub m. And conversely, if W is a subspace of the vector space V, such that u sub I is contained in W for all I, then u1 up to u sub m is in W for all numbers of this form, vectors of this form. So u1 up to u sub m, the subspace, is contained in W. So this subspace has the property that it contains each of these subspaces. And any subspace that contains each of the subspaces contains this. So this has to be the smallest subspace with this property. Now, I have to say that if the only mathematics you've taken up to this point is calculus, or then you probably haven't seen these kinds of mathematical arguments before. But once you start taking 300 level math classes, this is basic mathematics, the method of mathematics, what mathematics is, and you have to sort of learn how to think about these more or less abstract vector spaces and prove things about them. And it takes some time, it takes a lot of work. So you really need to spend a lot of time studying, especially studying the book and the examples in the book. Now, let me just repeat the definition of a sum of subspaces. So we have subspaces U1, U2 up to U sub M contained in V, and the sum of the subspaces is U1 plus U2 up to U sub M, which is the sum of all vectors, the set of all vectors of the form U1 plus U2 plus U sub M, where UI is in the subspace U sub I for all I from 1 up to M. Now, there's nothing unique about this representation in general. But sometimes it is, and we give that a name. So this is a very important definition. The subspace U1 plus U2 up to U sub M is a direct sum of the subspaces U1, U2 up to U sub M. If each element in the sum has a unique representation in the form U1 plus U2 and so forth plus U sub M. And the notation for a direct sum is U1, and we just put a circle around the plus signs. So this means the following: U1 up to UM are subspaces, and we look at the sum U1 up to UM, U1 plus U2 up to UM, and every vector in that has a unique representation as the sum of elements of U1 up to U sub M. So let's look at a couple of examples. So R3 is always a nice example. So this is F3. So my vector space is F3. And suppose I take U to be what we would think of the XY plane. That means all vectors of the form XY comma 0, where X and Y are in F. So this is U. And suppose I let W be the Z axis, everything in the form 0, 0, Z for Z in F. So what is the sum U plus W? It's all vectors that I can write as the sum of X, Y, 0 plus 0, 0, Z for any X, Y, and Z in my field. But when I add these two vectors, I just get all vectors x, y, z. So this is just the whole space. This is just saying if you take the xy plane and the z-axis and you add them, you get all of space. And the only way to write x, y, z as a sum of two vectors from u and w, so I should just say, moreover, the only representation of x, y, z in u plus w is xy0 plus 0, 0, z. There's no other way to break this down as a sum of two vectors where the first two coordinates of this vector is 0 and the third coordinate of this vector is 0. So this representation is unique. So therefore, F3 is the direct sum of u and w. Let's look at a couple more examples. Suppose I take my vector space to be R2. Just the XY plane. And I let U, for example, be the x-axis. Everything in the form x comma 0, x and R. And I let W be, let's say we take the line y equals x. So what I have here is, this is U, and this is W. So what is the sum set U plus W? Let's see. Let me write this as everything in the form U comma 0, U and R. And this everything in the form V comma V, V and R. So this is all vectors that I can write as U comma 0 plus V comma V. Which is all vectors U plus V comma V. And I claim this is all of R2. You get everything. So that XY be in R2. Can I write XY in this form? U plus V comma V? Well, if so, V, Y has to equal V, and X has to equal U plus V. But if Y is V, U plus V is U plus Y. So this means U has to be equal to X minus Y, and V has to be equal to Y. So, in fact, every vector x, y is in this subspace, and in a unique way. So, right, because if I take U comma 0 plus V comma V, where U is x minus y, so x minus y comma 0 plus y comma y. When I add them, I get xy. So therefore, R2 is U direct sum W. What's an example where you have a sum that's not a direct sum? So let's look at the case of that. Let's stick with our R2. So U is the x-axis. So that's U. W was the line XY. Let me call this again, U comma 0, U and R. Let me write this as W comma W, W and R. So this is my subspace W. Let me take a third subspace. Let me just call it maybe T. Maybe T is the y-axis. So T is everything of the form 0 comma T. T and R. So I have three subspaces, 1, 2, 3. And what is the sum space? I take the sum set, U plus W plus T. This is everything of the form U comma 0 plus W comma W plus 0 comma T for all scalars, real numbers, U, W, and T. So this is everything of the form U plus W, W plus T for U, W, and T. And of course, this contains U plus W. So this is everything. This is R2, right? But the sum U plus W plus T is not a direct sum. So for example, let me just take a random vector. 5 comma 8. Can I write it as a sum of in this form? Well, let's see. 5 comma 8 I could write as 2 comma 0
Can see.
plus 3 comma 3 plus 0 comma 5, right? This is in U. This is in W. This is in T. If you check my addition, this is 5 comma 8. But I can also write this, for example, as, I don't know, 1 comma 0 plus 4 comma 4 plus 0 comma 4. This is in U, this is in W, this is in T. And these are different. Different summands. So I can write this vector 5 comma 8 as a sum of vectors in U, W, and T in at least 2 different ways. Well, 2 means more than 1, so this is not a direct sum, right? I have U plus W plus T is R3, but not U direct sum W direct sum T equals R3. Right, so. And there are some other examples of this in the book. And direct sums turn out to be very important in linear algebra. And I'm going to describe two more properties of them, and then actually we'll be done for the morning. So let's take a look at that. So this is the statement in 1.44, condition for a direct sum. So suppose we have U1, U2 up to u sub m subspaces of V, then U1 plus U2 up to u sub m equal V is a direct sum if and only if, that's what this double arrow means, the only way to write zero as 0 equals U1 plus U2 up to u sub m is if u sub I equals 0 for all I going from 1 up to m. So we know these are subspaces, so they all contain 0. So you can always represent 0 as 0 plus 0 plus 0 plus 0. And if that's the only way to represent 0, then in fact, for every element in the vector in the sum, there's a unique way to write it as a sum, as you have a direct sum. So of course, if the sum is direct, then this is a representation of 0 and it has to be the only one. So it's only the converse that we have to prove. So let's say, suppose 0 equal U1 up to u sub m with u sub I and u sub I for all I implies u sub I equals 0 for all I. So let V be in the sum. So let V be U1 plus U2 plus u sub m, be one representation of V as a sum of elements in this set. And suppose we also have V as V1 plus V2 up to V sub m, where again, all the V sub I are in V. So I have on the surface two different ways to write V as a sum of elements of these subspaces U. But then I subtract U minus U. U minus U is 0. This is U1 up to u sub m minus V1 plus 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 V sub m. When I subtract, I can rearrange this. This is U1 minus V1 plus U2 minus V2 plus u sub m minus V sub m. And this is in U1, and this is in U2, and this is in UM, and so on. So this is a representation of 0. But the only way that can happen is if U1 minus V1 is 0, U2 minus V2 is 0, and so forth, which means U1 equals V1, U2 equals V2, and so on. So these have to be exactly the same representation. So if the only representation of 0 as a sum is sum of zeros, that implies your sum is a direct sum. So that's theorem 1.44. And something very similar to that, when we're dealing just with two subspaces, is the following. So if we have U and W subspaces of a vector space V, U plus W is a direct sum if and only if the intersection of these two subspaces, everything that's in all the vectors that are in both, is 0. So how can we prove this? Proof. We have to prove that if U plus V is a direct sum, the intersection is 0. And we have to prove if the intersection is 0, then we have a direct sum. So let's prove the statement going from left to right in this direction. So suppose U plus W is a direct sum. Let V be in U intersect W. So this means V is in U and V is in W, and the V is in W minus V is in W. So therefore, V plus minus V is in U plus W, and this is the 0 vector, V plus minus V. But we also have 0 is 0 plus 0. So the fact that we have a direct sum means there's only one way to write the 0 vector. So V has to be the 0 vector. So the only vector in U intersect W is the 0 vector. So if the sum is direct, the intersection is 0. Any questions about this? Again, if you're new to sort of mathematical reasoning, it takes a lot of time studying by yourself in a quiet place to understand what's going on. Okay, we have to prove the converse. Suppose U intersect W is 0. Suppose 0 is U plus W with U and U and W and W. This means that U is equal to minus W. Which is a vector in U and W, which is the 0 vector. So that means U is 0 and W is 0. So what we really have is the only way to write 0 as a sum of something in U and something in W is 0 plus 0, which means we have a direct sum. We proved a moment ago that a sum of subspaces is direct if there's only this representation of the 0 vector. Okay. Any questions about this? Really, this is hard stuff to think about if you're new to this. But this is exactly what you have to learn in a 300 level math class. Okay. All right. So I'm going to stop at this point. The assignment's been posted. It's problems from the book covering the sections of chapter 1 that we've spoken about. And I will have a problem session on Friday morning. And if you have questions about anything we've been doing, anything in the book, any homework problems, then just log into the Zoom session and we can talk. Okay.
You said Thursday morning. Or
No, Friday morning, I'm sorry.
Friday. Okay.
Yeah, Friday morning, roughly 10:30 to 11:30. But I'll send out an email of this. Okay, then we're done, everyone. Be well. Stay warm.
Thank
and
you.
healthy. All right, bye-bye.
Okay.